Have you ever wondered what came first? Well, not the chicken or the egg. I mean, what really came first in the grand cosmic story? Before the stars blinked on, before the galaxies swirled into their magnificent spirals, what were the building blocks? We think of atoms as the fundamental pieces of everything we see, from the chair you're sitting on to the distant planets. But what if the universe started with something far stranger, far more powerful? Imagine seeds, not of plants, but of pure gravity. Tiny, ancient black holes, born in the first moments of time itself. We call them primordial black holes. This idea flips our cosmic perspective upside down. The very first complex objects in the universe weren't atoms, molecules, but microscopic pockets of collapsed space-time. Think about a regular black hole, the kind we see on the news. Behemoths formed from the deaths of massive stars. The end of a star's life story. A primordial black hole is the opposite. Not an end, a beginning. A relic from before stars existed. A fossil from the universe's infancy. To understand where these cosmic seeds come from, you have to travel back in time. Way back. Forget billions of years ago. We're talking about the first fraction of a second after the Big Bang. At that moment, the universe wasn't the cold, dark place it is today. It was unimaginably hot. It was unimaginably dense. It was unimaginably turbulent, a soup of energy and exotic particles. It was a cosmic pressure cooker, expanding faster than the speed of light. The universe was a chaotic, churning inferno, a place of pure potential. The laws of physics were being written on the fly. It was less a place and more an event, an explosion of space-time itself. Within this primordial chaos, things weren't perfectly smooth. Like a pot of boiling water, hotter spots, cooler spots. The early universe had regions slightly denser than others. These weren't big differences, just tiny fluctuations in the cosmic fabric. But in the Big Bang's extreme environment, tiny differences had enormous consequences. In some of these slightly overdense pockets, the inward pull of gravity was overwhelming. It could conquer the outward push of the expanding universe. A cosmic arm wrestling match. In these select spots, gravity won. When gravity won, the matter and energy in that tiny region had nowhere to go. It couldn't escape. It was crushed down into an infinitely small point. A singularity. A black hole was born, not from dying stars, unlike modern black holes, created directly from raw energy and density of the early universe. This could happen on many different scales. Mass of an asteroid. Mass of 100 suns. These primordial black holes were born not in death, but in the fiery crucible of creation, incredibly fast, in less time than a blink. In the first second of the universe's life, a whole population could have popped into existence, scattered throughout the expanding cosmos like black pearls on a velvet cloth, silent witnesses to the universe cooling down, witnesses to the formation of the first atoms, witnesses to the long, dark ages before the first stars ignited. They are the universe's oldest inhabitants, carrying secrets within their event horizons. They are time capsules from a moment we can never directly see. So the universe is now seeded with these tiny, potent black holes. What happens next? For millions of years, not much. The universe is dark, filled mainly with hydrogen gas. It's also filled with helium gas, and perhaps these primordial black holes. But they are not idle. They are patiently waiting, gravity quietly summoning. Slowly, the gas begins to feel their pull. A primordial black hole is like a gravitational kernel, a point of attraction. It starts gathering diffuse gas. It also pulls in dark matter. It becomes the center of a growing cosmic snowball. This is how they could seed the first stars, and seed the first galaxies. Without them, clumping and fusion ignition could take much longer. A primordial black hole gives a head start. It's a pre-made gravity well. Gas falls in, compresses, and heats. Pressure and temperature rise until the first star ignites. Those stars would be colossal, brilliant blue giants. They burn through fuel in just a few million years. At the heart of some, a primordial black hole may sit. On larger scales, these could be the architects of galaxies. Clusters of primordial black holes pull in gas. They pull in dark matter. They merge and grow into supermassive black hole seeds. The Milky Way's Sagittarius A might be one such grown seed. Galaxies form around these gravitational anchors, cosmic cities around citadels. This idea also offers a solution to dark matter. About 85% of matter is invisible. We feel its gravity. What if dark matter isn't exotic particles? What if it's primordial black holes instead? A vast population, from asteroid mass up to star mass, would collectively exert that pull. The idea is beautiful, it's elegant, it solves a lot of problems. But in science, beauty isn't enough. We need evidence. How do you find something that is, by its very nature, small, dark, ancient? You have to get clever. You have to look for the ripples they leave in the fabric of the cosmos. One way is through gravitational lensing. As Einstein taught us, mass bends light. A primordial black hole, even a small one passing in front of a distant star, would briefly bend its light, making the star appear to brighten. By monitoring millions of stars, we can hunt for these telltale flickers. Another way is to listen for their echoes. When two black holes merge, they send out powerful ripples in space-time. Gravitational waves. LIGO and Virgo have detected stellar mass mergers. If primordial black holes exist and merge, they'd produce a persistent background hum of gravitational waves. Detecting that faint signal would be like hearing the whisper of the Big Bang, a direct confirmation that these ancient objects are out there, colliding in the dark. And here's a surprising fact. Stephen Hawking said black holes aren't entirely black. Over immense timescales, they can slowly evaporate, emitting a faint glow called Hawking radiation. For huge black holes, this is painfully slow. For a very small, primordial black hole, say the mass of a mountain, the process would be much faster. Such a black hole born in the Big Bang could be ending its life right about now. Its final moments would be a brilliant flash of gamma rays, a final firework before it disappears. Finding such a flash would be smoking gun evidence. So, are primordial black holes real? We don't have the final answer yet. We are explorers mapping an unknown country. We are building better telescopes. We are building more sensitive gravitational wave detectors. We are running massive computer simulations. Each new observation, each new piece of data, brings us a step closer to knowing. The search connects us to the most profound questions. Where did we come from? What is the universe made of? The quest to find these cosmic seeds is a quest to understand our place in the cosmos.